I have the privilege of introducing the next speaker, Dr. Neetu Kumari. Dr. Neetu Kumari is an associate professor of applied mathematics at IIT Mandi in Himachal Pradesh, India. She is a Roman fellow and holds a PhD in applied mathematics from the Indian Institute of Technology, ISM Dhanbad, along with an MPhil and MSc in applied mathematics from the same institution. Her research focuses on mathematical biology and ecological modeling, including topics such as infectious disease dynamics, pattern formation, and the impact of pollution on disease spread. Dr. Neetu Kumari has received various awards and has teaching experience in mathematics-related courses at IIT Mandi. Today, ma'am will be speaking on the topic, Understanding Dynamics of COVID-19 in India using Data-Driven Model. Over to Madam Neetu Kumari.
Thanks a lot for such a nice introduction. So, my voice is audible, right?
Yes, ma'am.
Yeah, okay. So, my sincere apologies for not being able to attend in person this conference, and I would like to thank Dr. Vamsi for conducting this first conference of this consortium that has we are all members of. So, without wasting any time, I would like to share my slides, and I would like to just confirm once how much time I have for this presentation.
You have the 25 to 30 minutes time, madam. The time
Okay,
allotted
right.
to you. Yeah, we have that.
Okay, thank you, thanks. So, is my slide visible now?
Yes, madam. Perfect. You are loud and clear.
Okay, thanks. Yeah, so I'll be talking today about the understanding the dynamics of COVID-19 using a data-driven model approach. And we are all aware that COVID-19 has hugely impacted within the nation as well as globally in many terms, including economy and health. And in our research group at IIT Mandi, we had conducted some studies, some research articles based on the compartmental models, where we try to understand what is the effect of various societal factors on several parameters on this COVID-19 disease. And we were actually successfully able to model that also and understand it. However, we at some point realized that we were not able to capture the spatiotemporal pattern of the disease spread, pandemic spread. That actually motivated us to conduct this particular study, where we are talking about a data-driven model for understanding this COVID-19 epidemic, and for that purpose, we have considered this case study of India. Also, I must mention that this study is being conducted jointly with one of my PhD students, Kanav Rana, and this particular work is published, and all the details of this presentation can be found in this particular paper. Still, in case of any query or any concerns, please feel free to write to me. So, in this talk, I will be first talking about the two basic algorithms that we have used to study the COVID-19 data in India. So, one is the dynamic mode decomposition, and the other one is an extension of this DMD known as compatible window-wise dynamic mode decomposition of CWDMD. So I'll talk in detail, in brief about these two algorithms, and then I'll go ahead and we'll talk about various results that we have obtained for the case of India. So that includes magnitude and phase analysis. We conducted the error analysis to see how accurate the algorithms are, and we have also used these algorithms to reconstruct that data. So as I mentioned, there are several studies using compartmental modeling approach, and this is one of the most popular approaches that is being used to understand any disease dynamics right now. These models are very useful, and it helps us to understand the temporal dynamics of particular disease very well. It also gives a fairly good idea about how various factors impact the growth of the disease. And we must not forget that during these compartmental modeling, we do lots of assumptions for the model formulation in order to even fit the data and in order to rightly describe the dynamics of the particular disease. And this, we cannot deny the fact that this may affect the results. So one of the studies that we conducted, me and my PhD student Sumit Kumar, we have done. I'm just showing that one here very briefly. So here what we have done is we have divided the entire population into 6 compartments, as we can see: susceptible, exposed, quarantine, infected, isolated, and recovered. And this is how the flow of the dynamics along these compartments looks like. So with this study, we actually modeled the spread of the COVID-19 disease for the duration of April 2020 to February 2023. And this is quite, we were quite amazed and happy that for this such a longer duration, this one particular model is able to successfully predict the dynamics. So as we can see from this figure 1, the red dots are showing the original data, officially reported cases of the COVID-19, and the blue line actually is showing the simulated number of cases from the proposed mathematical model. However, where this particular model was lacking was that we're not able to tell what is the special spread of the disease among the various districts or various neighboring states. So that led us to go for a data-driven model. So in the data-driven model, first of all, the benefits that we thought the data-driven model can have is that it has a reduced mathematical complexity. Also, the problem of estimating the parameters using the compartmental model, that if there is any error in this estimating these parameters, that might affect our result. That was neglected in this method. So here we have used the DMD technique for this model purpose. So this DMD is a recently developed technique. It's a dimensionality reduction technique, and it is quite popular in the CFD community. And in the year 2015, Proctor and Eckhoff, in one of his papers, mentioned that this particular technique can be very successfully used to understand the spread of any epidemic. However, till date, the DMD technique has not been taken into consideration for understanding the COVID-19 epidemic in India. So I would like to come to in very brief, the basics of this DMD technique, what we do here. So here we first of all construct a data matrix X, as we can see here. So we write our data in the form of this matrix X, where each of the entries x0, x1, x2, xm, it is of the form Rn. And we further what we do is that we rearrange this data set into the form of x and x dash. So essentially these two are the same data set, but x dash is one time step ahead of x. And after rearranging this data set in this particular form, we use the algorithm, which I will mention right now. So our data set consists of 640 Indian districts. And the duration that we have taken for this study is from April 2020 to October 2021. And in these matrices, the columns of this matrix comprises of the dates, and the rows actually it comprises of the districts. Now this is the data set A. So this data set A looks something like this. So here we have 640 districts of India that we have considered, and it is the number of confirmed COVID-19 cases these are the entries of this matrix, and the dates are actually the columns of the matrix. Now this data set A we can definitely use to understand the spatiotemporal pattern of the disease. However, it will not give a very clear picture because of the number of attributes to be so high, 640. So we decided to convert this data set A into data set B. So data set A we picked up from the government site, and we converted it to data set B. So now the data set B actually has a less number of rows. We have 36 states. We added up these districts, and we have all the cases for these 36 states. And similarly, the columns we consider to be weeks. So we had 79 weeks. So the data set B will be using to understand the spatiotemporal dynamics. So this is how the data set look like in the case of the data set B that we prepared. So it looks something like this. So now we have the data set B. Now we wanted to apply this DMD technique here to for that purpose. So what we want to do is that we have this xk plus 1 time step ahead of xk, and we want to obtain this operator A, linear operator A. So it must satisfy this relationship xk plus 1 equals to A times xk. Now, depending upon the data, it can be assumed that the operator A might not be exact. Hence, the relation in equation 1, it can be further written as x dash approximately equal to ax. And then it can be obtained by this formula. So, the algorithm of this DMD, it goes something like this. So, it consists of 4 steps. The first step includes calculating the singular value decomposition SVD of x. Once we get that x, now the next step is to obtain A by computing the pseudo inverse x plus. Again, we use SVD for calculating the pseudo inverse, and we get the value of A, matrix A. Once we have got the matrix A, now we want to obtain the reduced matrix A tilde. So we obtain the reduced matrix A tilde by diagonal truncation. Once we have A tilde in our hand, we perform the eigenvalue decomposition or spectral decomposition to obtain the diagonal matrix lambda and the corresponding eigenvector matrix W. Once we have these in hand, W in hand, the next step is to reconstruct the high dimensional solution. This means we are actually finding out the DMD modes by this step. So once we have obtained the DMD modes, the next step is to identify whether how significant these DMD modes are. This means how effective these DMD modes would be, that we have to choose out of the several DMD modes that we obtain from our data matrix. So for that, what we do is that we calculate its frequency, time frequency we obtain, we have calculated, and using this time frequency and XDMD, that is the reconstructed DMD modes, XDMD, we use this to further obtain the power. So I'll just, the frequency that we get is using this equation Fk, here mentioned in equation number 3. And the reconstructed DMD modes, XDMD, is obtained using this phi exponential omega d of d. So here b is the initial amplitude, and it can be obtained using this particular formula. B is equals to pseudo inverse of phi x naught. So that, of course, we can obtain from here, given equation phi. Once you have got the reconstructed DMD modes and the frequency, now we apply the compatible window-wise dynamic mode decomposition. So now this is, of course, again, it is another algorithm. Here, it's a modification where what we do is that we modify the DMD technique and we apply it again. So here what we do is that we have, when do we apply the CWDMD is the case whenever the data set is not compatible for applying the DMD, then we go for CWDMD. And what do you mean by not compatible? I'll just talk about it in a short while. So here what we do is that we divide the entire data set into compatible data sets. And once we have, so for that we choose different multiple windows. So once we have several windows are chosen, we obtain the consistent data sets, and it is given by xk and xk dash. And once we have this data set, we apply the DMD algorithm again. So when I talk about not compatible, when I say the data set is not compatible for applying the DMD, so when is that? So let us talk about what do you mean by compatibility for DMD. So here the DMD is compatible. So whenever you data set X with temporal resolution n plus 1 and spatial resolution n, then the data set is compatible whenever n is greater than or equal to m, or we can say m is less than or equal to n. Whenever this happens, then we know that we can actually apply the DMD there. And what happens, what does it ensure when this happens? This ensures that the data would be linear and consistent. For that purpose only, this compatibility is required. So once we have divided our data set into multiple windows, which is compatible, then we go ahead and apply algorithm 2, which is our algorithm for compatible window-wise DMD, CWDMD. So here, as I said, once the data set has been divided into multiple data sets, multiple compatible data sets, then we apply the algorithm 1, that is algorithm for the DMD. So further what we do, once the DMD algorithm we apply, we obtain the power of each of the DMD modes. And as I mentioned, the power of the DMD mode is very important because that will only decide whether a given DMD mode has how much impact that given DMD mode has on the spread of the disease or on creating the dynamics of the data set. So that only the power can tell. So the power we obtain using this formula, lambda. So this is for 5J DMD mode. This would give us the power of the given DMD mode. Higher the power, higher is the significance of the DMD mode. Now, once we obtain this power, based on its power, we choose the most dominant modes. And this modes can be categorized into 3 types. The first one is decaying, second is oscillatory, and the third one is growing. So, as the term itself suggests, whenever we have a decaying, the dynamic mode is of decaying type, this will tell us that the disease is going to decay in due course of time. And when it's growing, then it is going to grow in the due course of time. So, yes, and then we have done the magnitude analysis, phase analysis, and the error analysis. So the magnitude analysis actually, based on the magnitude of all the states, the higher the magnitude, higher would be the number of cases in that particular spatial location. And the phase difference, so the phase difference actually would give us, so the formula is given here. So what actually the phase difference or phase analysis would tell us is that it will tell us what is the time lag between the peak of the disease between the 2 states. So that would be determined by the phase analysis. And the error analysis, of course, as obvious, it will be telling us how accurately we have applied the technique on the given data set. So what we have done is that we have divided our data set B that we reconstructed from data set A, which was of higher dimension. So for, the data set B we divided into 26 weeks. Each of we divided into 3 windows, and each of the window consisted of 26 weeks. And then we applied the CWDMD there. And we made sure that there was no overlapping of the windows, and the results were not influenced by the choice of the data. So let us come to the results. So here, this is the first window that we have chosen. So it is from April 2020 to October 2020. So this is the standard stem plot that we have done for our dataset B, the first window of dataset B. And we see that out of the several DMD modes, we found that DMD mode 1 and DMD mode 2 were the 2 DMD modes which had higher power, and hence it was much more significant for the study. So we used these 2 DMD modes 1 and DMD mode 2, and we obtained the spatiotemporal pattern for both these modes. So mode 1, this is figure B is for mode 1, and figure C is for mode 2. So we can see we have performed the magnitude analysis here as well as the phase analysis. So here this is showing the different phases of these states, each of these states. And this is the real data, original data from the official site, the confirmed cases of each of these important states. We have not got here all the states, but just important states where we are seeing that the dynamics is interesting. So what do we see from here is that from this mode 1, the magnitude and phase analysis, magnitude analysis especially, we see that Maharashtra has the maximum number of cases. And from mode 2, we see that Andhra Pradesh has the highest number of cases during this duration. And apart from that, we also see that the phase, so this actually matches with the real data, as we can see. And we must note here that both mode 1 and mode 2 lies outside this circle, so it's in a growing mode. And since it is a growing mode, it is reflecting the fact that this is going to grow in the coming durations, in the coming course of time. So also we saw from the financial analysis that Tamil Nadu and Karnataka, it also stand close, being considerably high as compared to the magnitude of the other states. And the possible causes that could have been responsible for high cases in these states could be the migration of the workers in that duration of time. Now the phase analysis, here comes the special pyramid pattern. So the phase analysis, when we conducted, we found that the time lag between the peaks of Andhra Pradesh to Maharashtra, Delhi, Karnataka and Madhya Pradesh is between 3 to 4 weeks. This means that if the peak is coming at nth week in Andhra Pradesh, so here n is 90, then the peak can be seen in Maharashtra, say 22 or 23 weeks. And similarly, we are able to find out the time lag between the peaks of Tamil Nadu to Maharashtra or Karnataka, Delhi and Madhya Pradesh was between 4 to 5 weeks. And it actually complied with the data, the original data that was collected. So, and not just that, we can actually calculate this time lag between the peaks between any of these states with respect to any other state. So this actually, at one time, it is telling us how much confirmed cases we are going to have, when it's going to have the peak at one state, at one given state. But at the same time, it can also tell what is, after how many weeks we can see possible chance of peak in the neighboring state or any other state. So that actually had an upper hand over the compartmental modeling that we do. Now the second window that we chose was between November 2020 to April 2021. And we performed again, this is a stem plot, and we see there, we found these two, mode 1 and mode 2, to be the significant modes here based on their power. And for these mode 1 and mode 2, again, we saw that these modes are of the growing wave. We obtained the truth and the phase analysis for these two modes as well. And we saw that in the cases of Maharashtra, Delhi, UP, Kerala, and Karnataka, the cumulative confirmed cases were substantially higher using these two modes. And it was also reflected in the original data that is shown here. Then we further went ahead and did the phase analysis. So we did the phase analysis for the first week. So the phase that I'm showing is for the first week. So it is near about 3.39 weeks for the phase difference between Maharashtra and Arunachal Pradesh. Similarly, the phase difference between Arunachal Pradesh and Ladakh was found to be nearly 2.6 weeks, and hence it was compared to the original or official data reported. Now, the third window that is we chose was from April to October 2021. And here, interestingly, what we see is that the modes that we are obtaining is of decaying nature, as we can see from here. The most powerful modes are of decaying nature, which gives us some hint about the pattern of the disease that we're going to get over a period of time. Now, for these two modes, we obtained the magnitude and the phase analysis, and from this, we are seeing that the maximum number of cases are seen in the state of Kerala, and it resembled the real data as well, as we can see from here. And for the mode, from the mode 2, we could say again here, the Kerala was had the highest number of cases, confirmed cases. And next in line is Maharashtra, Tamil Nadu, and Karnataka. They also had considerably high cases, as seen from magnitude analysis, and it resembled the original data as well. The phase analysis, when we did, we were able to find out the time lag or the phase difference between Kerala and Nagaland was approximately 18 weeks or so. And between Assam and Kerala, it was near about 7 weeks, and it actually matched with the real data. When we checked it, it was matching with the real data. The peaks that were seen in these states were close to what was what we are calculating. So this was quite interesting as we were able to see the statistical patterns. Further, here what we have done is that we have done the data reconstruction. So we have used data set A for reconstructing the data. So here we can see from the figure A, so this is the number of districts versus the date. So the number of red dots that we see, it is the official data that has been reported. And the black line that is showing here, it is showing the reconstructed data. So we can see that for these districts, very accurately, DMD technique can be used to reconstruct the original data. So we must not forget that the data set A was compatible for applying DMD. However, we chose to construct data set B because of the more clear picture of the spatiotemporal pattern. Now, for the data set B, again, we have used a CWDMD, and for using CWDMD, we have reconstructed the data set here. So the red dots here, these are the original official data set, officially reported cases of COVID-19, cumulative cases, and the black line is showing the simulated data using the CWDMD. So here also we see that the CWDMD is pretty well able to reconstruct the data and can be successfully used for prediction, although we haven't used here in this work for prediction, but it can be successfully used to predict the future patterns. Now here we are actually showing the real-time data reconstruction. So the first figure, we can say figure 7, is the data reconstruction for using the DMD for districts, and the second one is the data reconstruction for figure 8 is the data reconstruction for the states. So we can see that the original data and the simulated data, it's near about same, not exactly same I would say, but it's nearly same. So data reconstruction also is very successful. This means we can very well use these techniques for prediction of the for the disease. Yes. Then next we perform the error analysis. So the error analysis here we have shown that for data set B, the data set B, we have used the error analysis using DMD and CWDMD. So as we can see that the data set B is not a compatible data set for for DMD. A reason being that the number of rows is smaller than the number of columns. So we have applied here DMD, and we can see clearly that whenever the compatibility condition is not being satisfied, then the error using DMD is pretty high. However, that is not the case with CWDMD. That is, it is giving a fairly accurate result. I won't say exact, but yeah, fairly accurate result. However, whenever the compatibility condition is being satisfied, that is data set A, then DMD is capable of giving very accurate result with a very low error. So, so the conclusion is that there has been several studies for understanding COVID-19 in India. However, the DMD and CWDMD marks a significant step towards understanding the spatiotemporal dynamics in particular for the disease. Also, we can see from our study that in spite of having challenges like migration and unpredictability of the virus, this technique or this algorithm has been able to fairly accurately predict the cases of the COVID-19. Also, we must mention here that this CWDMD method, we have improvised it by using the rank truncation here. We have improvised it, and the result also we can see is fairly more better than the previous result that exists in the literature. And we can actually combine this DMD and CWDMD techniques with other machine learning techniques, and it can be used to understand the dynamics of other pandemic. So, yeah. So these are some of the references that has been used. And that's it. Thank you. So I think I finished in 25 minutes.
Thank you, madam.